as well as Gregory Bachelor, the design Gregory Bachelor. Thank you so much.
This way. And that's no force. So this force over here is our volume. That's all.
Then you say two
Less legible.
so this was two
Yeah.
This is pretty good.
Alright.
Two.
Alright, here we go.
Where you want to-
At times.
No, it's because the asthma. You can't only do it for this not.
Good afternoon, a reminder, all students should be under the supervision of an adult at this time, and a reminder to those students in the stairwells that we do have cameras on you.
So you're right, so this minus that would equal
Once
the
again,
amount times this.
students should be in the supervision of an
If you
adult.
wanted to, you could have gone all the way backwards, back to the start here.
Sweep the hallways
And said, all right, well, what is this for? Well, it's,
Students out of the building, once
of
again.
course,
those
it's
of you in
like
the
one end times
stairwell,
that, so
We
yes,
see.
this would be F over 4 for that math, right?
She's repeated it
So
like
this would
three
be
times. It was funny to
Like,
three.
1/4, 1/4 F.
Some people
going
require.
backwards,
Multiple.
And then,
Reminders.
we'll have to do this right here. All right, so this minus 1/4 F is equal to.
Let's go.
Do this.
Even end of the thing.
All welcome to our second review session. Here, we're gonna be talking about forces and free body diagrams
Yeah, please.
and all that good stuff. So I did in fact post the first one on Canvas. I'll just show that off real quick. It won't be recorded in the video, that's fine. But there's a whole YouTube playlist right at the top. There's only one thing in it so far, but I will put the other ones in as we get there. All right, talking about forces. So we're gonna do this in a very similar way. We're gonna talk about generally speaking, figuring out how to figure out some key relationships and equations in forces, especially any that are not on the formula sheet. These are mostly on the formula sheet, so it's a little bit less of a concern. Talk about and practice drawing some free body diagrams and figure out when is it a forces question? When is it something that you need to tackle using forces versus another set of tools? The single biggest piece of advice that I can give you on the whole exam, ABD, FBD, always be drawing free body diagrams, right? On the multiple choices, sketch them out on the sidebar. For FRQs where you need them, a lot of times they'll ask you to draw them. But especially on some tricky multiple choices, there's nothing better than sketching a quick free body diagram, especially there's a few classic ones with elevators or like rotational motion or things where you really just want to sketch out a quick free body diagram so you make sure you know what you're talking about. We'll go over some key equations. We'll look at a few of the more challenging multiple choices on there. And then if we want, we can either continue to work on the stuff in the packet, or we can kind of brainstorm and think through a little practice FRQ that's mostly about forces. That might be interesting. Let me move this, otherwise I am gonna wipe out and run over it. All right. So let's kind of begin at the beginning with key things in forces. So Newton's laws, these ones are very, very, very important. Newton's first law, right? That's the objects at rest stay at rest and such. The best way to think about this is that anytime you have a velocity change, and that usually we think about that as like speeding up or slowing down. But it also applies even if your speed doesn't change, but your direction does. Any kind of change in velocity requires a force. If you weren't moving and you want to move, you need a force. If you were moving and your motion changes at all, you need a force. Speeding up, slowing down, changing direction, any of those requires a force. If you don't have any net forces, then you're sort of by definition not doing any of those things. Newton's second law is probably in the top 3 for most important equations of the year. That's our F equals ma. You'll see it on your formula sheet. Instead of writing it as F equals ma, they like to write it as A equals the net force divided by m. I think they write it that way for a couple of reasons. One, a lot of times you're trying to find the acceleration. The other way is sometimes people get the feeling from F equals ma that accelerations cause forces versus the other way around, forces causing acceleration. So, but in any case, it's the same equation, F net equals ma, and that one we use all the time. Newton's third law is one that people tend to not pay a lot of attention to. Yeah, for anytime one object applies a force to another object, an equal and opposite force gets applied back. This one is really important though, partly because it's going to help you fill out complicated free body diagrams if you can identify those action-reaction pairs. Also because, they change the multiple choice every single year, but as Mr. O'Neill can attest, there's certain types of questions that they give you every year. And one of those questions that I would almost be willing to bet is on the exam. Is at some point they're going to ask you a question like a big thing and a small thing are interacting, the whole Earth and a tiny satellite. F1 is the force that the Earth applies to the satellite, and F2 is the force that the satellite applies to the Earth. And they want you to make a judgment about those two forces, and your job is to be like, they're the same. They're always the same. There's no way for them not to be the same. In that. There are, of course, a lot of different types of forces, and the challenging thing about this unit on forces tends to be that even though the basic approach is always the same, there's lots of different forces they can throw at you. So we want to make sure we remember gravity. We're going here mostly with the good old-fashioned mg version of gravity rather than the big space
Sorry
gravity.
for the interruption. Gabriel Rodriguez, if you can make it to the main office. Gabriel Rodriguez, if you can make it to the main office. Thank you.
Forever immortalized in the video. So one thing to note with gravity, of course, is a lot of times they'll give you the mass in kilograms. Just be on the lookout. Sometimes they will be like, oh, here is a 30 Newton box. And it's important to remember that they've just straight up given you the weight, they've given you the force of gravity there. So just be on the lookout for whether they've given you newtons or kilograms for how big something is. Tension is very important. Tension, the big thing with tension is that we tend to assume that the tension at two ends of a rope is the same. There is one instance where that gets violated, that comes up a lot on the test. And that is if you have a pulley that has mass, this kind of buddies up with rotation a little bit. If your pulley actually has some mass, if it has some rotational inertia, you need a torque to get it rotating, which means these tensions have to be different. There has to be more tension on one side than on the other to let the wheel rotate. If your wheel, on the other hand, has no mass, then you can just move it around however you want. Then the tensions are going to be the same throughout. So typically, we sort of make the assumption that the tensions are the same on either end of the rope, with the slight exception of rotational problems where you have to have some torques involved. Friction comes up a ton. The important thing to remember with friction is that mu Fn equation, that your force of friction, they give it to you in kind of a complicated way in your formula sheet. They tell you that the magnitude of the force of friction is less than or equal to mu times the normal force. We sort of have to remember that there's two types of friction here. There's static and kinetic, right? Kinetic is the easy one. Kinetic is always equal to mu times the normal force. Static is the more complicated one, where it maxes out at mu times the normal force. It maxes out at mu times the normal force. A lot of times you'll have questions that are about static friction, but secretly they want you to do stuff where your static friction is maxed out. And we'll take a look at that. Springs do come up from time to time. There's that Kx force on there. And then, of course, centripetal forces, rotational motion does come up. We're usually going to use v squared over r for our acceleration, which means, of course, a centripetal force of m times a, mv squared over r. We know enough now with our unit on rotation under our belt that if we would rather write this as m omega squared times r, we can do that. If for whatever reason you have omega instead of v, those are both on your formula sheet. They give you the centripetal acceleration instead of the force, but F equals ma will help you figure that one out. The biggest thing to remember about centripetal force is it's not its own kind of force. You should never ever draw a free body diagram that has like centripetal force on it. The centripetal force always comes from something else, a spring or tension or gravity or a normal force. There's always something providing that centripetal force. Sometimes it's your job to figure out what it is, but that is a thing you always figure out. All right. There's a few cases that come up all the time. Inclined planes come up very frequently. Typically for inclined planes, though not 100% of the time, they're going to give you the angle there at the bottom. And it's really important to remember on an inclined plane, our directions of motion are usually like up or down the plane and perpendicular to the plane. That's kind of our X and Y directions, if you like. It's really, really helpful to remember that your parallel force of gravity, the force of gravity down the ramp is going to be mg sine theta in this case. And this one's going to be mg cosine theta. One of my students who graduated a year or two ago gave me the mnemonic sign for slide, and that has been a very helpful thing. So if you can have that, that's one of those ones that's gonna, I'm not the biggest fan of memorizing stuff. But that's one that if you have that in your pocket, it's gonna save you a lot of time on multiple choices, just be able to pull out mg sine theta and like go on your way. Yeah.
What are the two lines?
These?
FG two lines.
Oh, parallel. The force of gravity in the parallel direction or in the perpendicular direction. Great. Pulleys, again, the weird thing with pulleys is that we think of them as bending, we can think of them as bending our coordinate system. So like in this case, if this box is going to go down, right? If that box is going to go down, then this box is going to go up, right? So we can think of those kind of coordinated things. That's a fairly complicated scenario, but we do still get that sometimes. Every forces problem is going to have basically the same approach. You're going to draw your free body diagram. You're going to pick your directions of motion, and then you're going to set up Newton's second law in those directions of motion. You're going to write out F equals ma, and that's going to lead you to victory. That's going to lead you. All right. For drawing that free body diagram, I expect at this point in the year you're mostly like pretty good with simple free body diagrams. But if you encounter a more complicated question where you're not sure what's going on, we can remember that we sort of started with this agents and interactions model, where we started with the agents. Those are all of the things that are applying forces to your object. So typically there's two agents that we really need to worry about. Earth, whose interaction is gravity. And then from there, you're just going to list everything that's touching your object. So you'll list all of the strings and ropes and other boxes and surfaces and things that are touching. Most of these things only get to apply one force, right? Strings get to apply tension, springs get to apply spring forces. It is important to note that any kind of surface to surface contact has the potential for two forces, has a potential for a normal force and some kind of friction depending on how they're moving relative to each other. So if you get a very complicated scenario, you can fall back on like, okay, what the heck is going on here? And the nice thing about this model is if you write out this little table of agents and interactions, the interactions list is going to give you a list of all the vectors you need on your diagram. And so if there's like 5 things on your interactions list, you're going to write 5 vectors, and then you know you're done with that. Sometimes, but not always, they will ask you to draw vectors of like an appropriate relative length, similar to how they'll have you sketch graphs. Typically, it doesn't have to be perfect. If one is like twice as long as the other, it doesn't have to be, you don't have to get a ruler out. Newton's second law. But like you might be asked on like an Atwood machine problem, right? You've got like, you know, a small mass and a big mass to draw free body diagrams. You're good. You know, if you were going to draw them to scale, you'd want to draw like M2G and tension. And then for M1, you'd want to make sure tension was the same length, but that M1G was noticeably smaller, right? So sometimes they'll ask you to sketch free body diagrams to length. If they want you to do that, they'll give you a grid and they will be very specific that they'll be like the relative lengths of the vectors should match. If they don't tell you that they care about the lengths of the vectors, they don't care about the lengths of the vectors, just draw your free body diagram. If it's helpful to you to draw one vector longer than the other, go for it. That's totally fine. All right. A couple quick side notes. The exam, 99.995% of the time, wants you to draw vectors and not components. So if you've got a car that's driving around on a ramp, they would like you to draw the gravity vector down. Oh, great, it's in crash.
Ooh.
That's fine.
Wait, what was the list of three things?
Which list of three things?
Draw the free body diagram.
Draw the free body diagram, write out Newton's second law.
Pick direction.
Yeah, sorry, pick your directions of motion, right? So do you care about the horizontal or vertical? Or if you're on a ramp, your directions might be parallel or perpendicular to the ramp.
Three.
And 3 is right out. Because we care about what direction of motion we're looking at, right? If something's sliding down a ramp, we mostly care about we're gonna go ahead and know all of these. We mostly care about the parallel and perpendicular directions. All right, we're gonna go ahead and back to sharing our screen. In this case, there we go. Where were we? Right, so 99.9% of the time, they want you to draw just the vector. So if you've got this car on a ramp, they're gonna want you to draw gravity, they're gonna want you to draw a normal force. Maybe they're gonna want you to draw some kind of, static friction force or whatever. They don't want you to break it into components. They want the whole vectors. Now, obviously, it might be helpful to you to break it into components, in which case what you should do is break it into components off to the side, like sketch yourself a little one on the side so you can figure out all the sines and cosines. Don't put that on the main diagram. They will be like vectors, not components, on the prompt for the question, which means if you draw components, they will be mad at you because they told you not to do that. So, yeah.
Are you gonna go over how to put this out?
So, in general, they will label an angle that you can use. There's two main ways to think about sines and cosines, and we kind of touched on this during torques. One is to sort of do the trig here and to be like, hey, if this angle is theta, this angle is also theta, and like work your way around, like it was an SAT problem, like working your way around all of the little, well, this is theta and this is 90 minus theta, so this other one has to be theta again. The other way to think about it is you can think about what happens to the components of the force as you change the angle. So just as for the sake of argument, let's say I wanted to find the vertical component of this normal force. I wanted to find Fn in the y direction, right? Let's say, okay, in this case, it's pretty clearly going to be cosine theta because that's what's there. But let's say I couldn't figure that out. Imagine reducing this angle, right? You're making that ramp flatter. As I make that ramp flatter, my normal force should get more and more vertical, right? Yeah. Which means that the y component of that normal force should get bigger, right? Which trig function gets big when the angle gets small? Cosine. So I would be like, oh, this is Fn cosine theta. So sometimes you could follow that more intuitive way of being like, should that component get big when my angle is big or small? If the component gets big when the angle is big, that's sine. If the component gets big when the angle is small, that's going to be cosine.
I'm good.
Okay, you're good. You don't have to sneak around. Okay. So yeah, draw vectors, not components. All right. Before we get to some examples, there is one special case that we did way early in the year, before some of you knew how to do differential equations, that I want to talk about, which is this case of linear drag. And we talked a little bit about this earlier in the year. And sometimes they actually want you to know how to solve it. Mostly they want you to know kind of the general behavior and what it looks like. So let's say we've got an object that we're dropping, and it's got gravity. It's also subject to a drag force, and a lot of times they'll write this drag force as negative kV. That negative sign indicates that whatever direction the velocity is in, the force is in the opposite direction, right? So it's got a magnitude of kV opposite to our direction of motion. And we're going to assume here that we are going to start this thing from rest. We're going to drop it from rest. All right. Qualitatively, we might remember a little bit of what happens to this, which is that at first, when we drop it and our velocity is equal to 0, how much drag force do we get? none, right, basically. And so the thing is gonna have a fairly large acceleration downward. If we check back on it a little bit later, gravity never changes, gravity is still the same. But if we check back on it a little bit later, now it does have some velocity to it. And because it has some velocity now, there's a little bit of drag, right? And because there's a little bit of drag, what happens to our acceleration? It's smaller, it's still down. We're still speeding up, but our acceleration gets a little smaller. If we wait a little while longer, and our velocity is quite big, then our drag force will be reasonably big. And at some point, our drag force will be very, very, very close to what gravity is, at which point our acceleration will be
That terminal.
very, very tiny. And over time, our acceleration will shrink and shrink and shrink. And eventually, if we wait long enough, we'll hit a point where our acceleration is zero, at which point, if our acceleration is zero, our velocity will become constant. And this is what we call terminal velocity. In this case, we can actually write an equation for our terminal velocity, right? If our acceleration is zero, what does that tell me about my two forces?
Equal.
They're equal. So what I can write is I can go ahead and write whatever my terminal velocity is, kVt is going to equal mg. And so my terminal velocity is going to be mg over
Is
t.
that K of VT or K times VT?
That is k times vt. K is some constant, right? It's some coefficient that tells you, like a big parachute, right, has more drag than like a little ball. So it's some constant that tells you how much drag the thing has.
So what makes this different? Like, why is this a special case?
The reason it's a special case is imagine that we know that it starts at a velocity of zero and it ends up at a terminal velocity like this. And if we think about what that velocity versus time graph would look like, right? What would that velocity time graph look like?
Well, it's a 1 over something.
Well, so we started at a velocity of zero and we gradually approach terminal velocity. It would in fact look like that, which is it'll asymptotically approach terminal velocity. We've actually seen this graph before in a totally different context, like last week, which is, yeah, it's exactly the same graph. It's exactly the same graph.
Physics just.
Yeah, it's gonna asymptotically approach that. Now, every once in a while, they actually want you to figure out what actually is this function. What is that function? And we're actually going to go ahead and do that. We're going to solve this differential equation in this case. So let's go ahead and take a look at this. We'll go ahead and write our Newton's second law here, right? Our velocity is in the downward direction. So let's go ahead and take down as the positive direction. So I'm going to go ahead and write mg minus kv is going to equal ma. If I want to solve for my acceleration, I divide by m, that's going to be g minus k over m times v. And what we're going to do here is we're going to set ourselves up a little differential equation by remembering that acceleration, how does acceleration relate to velocity? dv dt.
Excuse me, Mr. Bates.
Yes, sir.
Can I borrow your Facebook?
Oh, yeah, absolutely. It's just in the stack. Yep. Of course. All right. So here is a differential equation. A lot of times they'll be like, write a differential equation that could be used to find the velocity. There's the differential equation. It's just an equation that relates velocity to its own derivative. We're going to solve this thing. And the way we're going to solve this is a separable differential equation, as all of the ones you'll be asked to do are. So what we're going to do is we're going to get all of our v's on one side. And all of our t's on the other. One of those sides is a lot busier than the other. And then we're going to integrate. We're going to integrate both sides. All right, the right side is very easy. Let's do the right side first. T. Of course, we should be responsible. These are indefinite integrals, so we should do plus C in this case. Now, my left side looks awfully complicated, but it's a bunch of stuff. It's dv over some stuff that involves v. And so hopefully this stirs that calculus thought in your brain that this, what kind of vibe does this give you for an integral? It gives you an ln vibe. Now I could do like a proper u substitution or whatever, and we could do this. Instead, we're gonna sort of play chain rule guess and check here. We're gonna be like, okay, what if it was ln of all this stuff, right? Is that good enough? Am I done? Well, if I take the derivative of that, I certainly get 1 over all of that stuff, right? But if I take the derivative of that, what would I get popping out from the chain rule? I would get an extra negative k over m. And so what I can do is I can sort of preload my chain rule to get rid of that thing that would pop out and put a negative m over k. That way, when I take the derivative, that negative k over m comes out, cancels out, and I get my original thing back. All right, excellent. We want to solve for v here. We want to figure out what v is. So I'm going to go ahead and do some algebra. I'm going to go ahead and I don't know why I drew an h. Ln of g minus k over mv. I'm going to go ahead and multiply both sides, in fact, by negative k over m. So I'm going to end up with negative kt over m. And here's where I'm going to do a little bit of calculus fudging, which is c was a number that we didn't know, right? Now it's still a number we don't know. It's just a different number that we don't know. It's just a different number that we don't know. It's still a mystery box. We've just multiplied our mystery box by something. We want to go ahead and get rid of the ln, so we'll go ahead and raise both sides to the e power t k over mv equals e to all of this business. And here's where we got to remember, and we saw this when dealing with the RC circuits the other day. That additive constant up top kind of turns into a multiplicative constant in the front. And the reason, again, it turns into that is I can rewrite this as e to the c, e to the negative kt over m. And instead of writing e to the c, I'm just going to declare e to the c to be some other constant a, just some other number. All right, we're very close to being there. We're going to do a little bit of algebra to solve for v. I'm going to k over mv is going to be g minus a e to the negative kt over m. And finally, what I'm going to do is I'm going to multiply by this. I'm going to get v equals mg over k minus, I'm going to leave this again as a for the moment, e to the negative kt over m. We're almost there. One thing we want to know is we do want to know what this number a is. We do want to know what this number a is. And one thing that we can do here is we can plug in what we happen to know. We happen to know that at time 0, for this particular case, my object wasn't moving, right? Yeah.
So the k over m can move to the other side. It doesn't affect the thing with the a.
Well, again, a was just some number we didn't know, and now sometimes we'll do this just to avoid having 7 different letters. We're just absorbing those constants into that. So if I imagine that I plug in 0 for t here, right? I get e to the 0, which is 1. So what I get for v of 0 is I would get mg over k minus a, but that's supposed to be 0. It's supposed to start at 0, which tells us that a is mg over k.
You can just multiply.
Right. And one of the things that we actually know is that mg over k is our terminal velocity. And so what we actually get for our terminal velocity is we get, or what we get, excuse me, for our velocity function here is v of t is going to be our terminal velocity times 1 minus e to the negative kt over m. which is very similar to our RC circuit expression for a charging thing. It's that same 1 over behavior. So one thing that they want you to know is occasionally they want you to know how to derive this.
Oh, that's where.
Yeah, they also want you to know what the graph looks like. So they want to make sure that you know that like if you drop something from rest, that the graph looks like that. What if I take something and I throw it down faster than its terminal velocity? Yeah, so if I started at too high a speed, it'll slow down because that drag force will be really high. Once in a while, and this came up on the practice exam, they'll give you a case where they'll be like, yes, this thing experiences a drag force of negative kV, but there's no gravity, right? They'll be like, there's a car on a road, and the car starts off at some initial velocity, and then it experiences a drag force, right? But there's no gravity, there's nothing pulling it down, it's just slowing down. Putting on our RC circuit hats for a moment. If there's gravity kind of pulling the thing down, so it speeds up like that, what do you think the graph looks like for a car that's just slowly rolling to a stop because of air friction? Yeah. It'll look like, it'll asymptotically approach stopping. Because the slower that car gets, the weaker the force that's slowing it down is. So as it slows down, there's less and less force slowing it down.
So could you hypothetically find the point where if you just like drop something from 0, throw it down? Didn't we do that?
Oh, you could do that. Would be, I mean, that would be an interesting experiment. But you could definitely do that of like, I'm going to drop a thing and I'm going to chuck a thing down and I'm going to make sure that they hit the ground at the same.
And we did something
Well, I think the
similar.
one you throw down will always hit the ground first, because it would always have a slightly higher velocity, but you could set up an interesting experiment that way. Yeah. You could set up an interesting experiment that way. So they definitely want you to know about the shapes of those graphs. All right. All right. How do you know when it's a forces question? A lot of times they will be very explicit. They will be like, what's the force? If they want to know what the force is, it's probably a question about forces. Sometimes there will be mass or acceleration. A lot of times they will just straight up ask you what's the correct free body diagram, draw a free body diagram. That's pretty clear what they want you to do there. A lot of times when friction is involved, it's either a forces question, sometimes it's a work question. But even when it's a work question, you need to be like, oh, well, I know that my friction force is like mu mg times d or whatever. So if friction is involved, usually I at least want to consider forces. Anything having to do with inclined planes or springs or pulleys or tension, a lot of times has a good chance of being a forces question. Rotational motion, and what I mean by that is specifically centripetal forces. If you remember off the practice exam that we took, the one about the car going around the track with the centripetal force and the total acceleration and that kind of thing, cars going around tracks, centripetal motion is often forces. A lot of times statics comes in, so anything that is not moving or moving at a constant velocity, you're going to be like, ah, my forces are balanced. And in fact, one of the key phrases that you should be looking for in prompts is when they say constant velocity or constant speed. That's something you should like immediately circle, because when they're like, oh, this elevator is moving at constant speed, you should be like, boom, I know that the forces are balanced. Whatever force is pulling it up and whatever force is pulling it down are exactly equal. So that's going to be one of those key phrases. Yeah.
What's the difference between velocity and speed?
Velocity is a vector, so with a direction, right? So if I'm going 60 miles an hour this way, and then I'm going 60 miles an hour this way, I have not changed my speed, but I have changed my velocity.
So if it says it's a constant speed versus a constant velocity, does that matter?
Usually in the context of the question, it'll be pretty clear what they're talking about. Constant velocity is the stronger. If it's constant velocity, it's just like it going in a straight line forever. A lot of times there'll be like a car is going around a track at a constant speed, or somebody's climbing the stairs at a constant speed or whatever, and then you'll know that the forces are balanced. So
What's the formula for centrifugal force?
that one's on. Remember, so the centripetal force, right? V squared over the centripetal acceleration V squared over R. So that's where, if we think about F equals MA, that's where we get that MV squared over R. That's good. All right, so we got a couple, these are, you know, a couple sample past FRQs here. This was a setup for an FRQ. It literally just has a force on there. These just, actually, this is a good side note. Velocities are not forces. And I know that sounds like a stupid thing to say, but like a lot of times they'll be like, you know, Thomas kicks a football,
Yes.
draw a free body diagram for the football while it's in the air. And a lot of times what people will want to draw, here's our football. It looks like a green papaya or something.
So weird.
Well, he kicked it really hard. A lot of times what people want to do is they're like, oh, well, the football is moving that way. And so they want to put a force that way, right? The thing is, it's left his foot. He's already kicked it. If it's flying through the air, the only force on it is gravity, right?
But then how do you, so there's no way to like indicate that it's.
If you can draw the velocity as like a separate vector, but a lot of times people want to be like, well, the thing's moving to the right, so I need to have an arrow moving to the right. Like if my car is moving that way but slowing down, the force is that way. It had been moving to the right, and so it still has some velocity, even though the forces and the accelerations are in the opposite direction. We got a couple other ones. You know, here's a spring, and they specifically give you a force. All right, we're going to take a couple minutes here to look at a few of these multiple choices. So I'm going to pause this recording, and then I want you to pull off a few multiple choices that you are particularly interested in going over, and then we will resume. All right, so let's take a look at a couple of these. Sometimes there's a couple different ways to attack these questions where you've got multiple objects. And one thing that I find that can be helpful is to kind of start by looking at the system as a whole. And what I mean by that is imagine taking these two objects and putting a box over them, right? So you can't see what's inside. And if you did that, what it would look like is it would look like when you pulled on that rope, it would feel like you were pulling one object that had a mass of 3 kilograms, right? I did. Of 3 kilograms, right? So what we could do is you can look at the system as a whole. You know you're applying a force F, right? F equals ma. In which case the acceleration of this system is just going to be F divided by 3 kilograms, right? Okay, so that's the acceleration of the whole system. And now we open the box. Because one thing we're guaranteed, because the objects are tied together, they have to have the same acceleration, right? They have to have the same acceleration. So now let's focus in on just the 1 kilogram block. And the reason I want to focus on the 1 kilogram block is, what does the free body diagram for the 1 kilogram block look like? Yeah, there's some stuff going on in the vertical direction, but in the horizontal direction, there's only one force. There's just tension, right? And in this case, we know that that force needs to apply the appropriate acceleration, right? Needs to give the appropriate acceleration. We know that the mass of this one is 1 kilogram, and we know what acceleration it has to have, which is F over 3 kilograms. So what does that tension force have to be? F over 3. It has to be F over 3.
You're right, because
That wasn't emotional.
What I think is neat about this is, let's imagine that we had instead talked about the 2 kilogram box, right? The 2 kilogram box is a little bit more complicated to do. Yeah, the two kilogram box, the 2 kilogram box has 2 forces on it. It has F minus T, right? Equals, well, again, yeah, it's got a mass of 2 kilograms. And it has to accelerate at a rate of F over 3 kilograms. So I need F minus T equals 2/3 F, which means the tension needs to be 1/3 F. That tension is 1/3 F. It's just that 1/3 F is speeding up the blue box and slowing down the green box. And what I think is kind of neat is if you look at the net force on each of them, the net horizontal force on this one is F/3. The net horizontal force on this one is 2F/3. This one's got twice as much mass. It needs twice as much force to accelerate at the same rate. But what I also think is kind of cute is 2/3 F and F/3 add up to F, right?
Yeah.
There's a sense in which the two boxes are divvying up the pulling force. And they're divvying it up in a 2-to-1 ratio because that's the ratio of the masses, right? How do you divide something? How do you divide something between two things where one gets twice as much? Well, one gets 2/3 and the other gets 1/3. So they're divvying up that pulling force kind of fairly amongst themselves. We wanted to look at number 9. Question number 9. Physics question number 9. That one, okay, there we go.
Yeah.
That's the musical cue we were looking for.
Something, or is that just?
It's just a song. It's called Love, yeah, Love Potion number 9.
Because I feel like they should make a musical based on that song.
I mean, ask the internet. I don't know. All right, so we got our thing. Now they've sort of kind of given us the makings of a free body diagram here. Like they've given us a picture, which is great. But let's go ahead and draw our free body diagram for our box. What should go on my free body diagram? Gravity.
No normal forces.
No normal force because we're not touching any surfaces.
Oh,
We're
we
not.
got tension to the left and tension to the upper
All right, we got T1 going this way, and we got
diagonally.
yeah. I'm gonna okay. Shh, I know that it doesn't quite line up with the strength, but it's okay. No components. We're just drawing the whole thing. Now, because this is a multiple choice question, I'm going to draw components all over it. When we're drawing components, what do we want to draw components up? Yeah, I guess which force do we want to break apart? Yeah, let's break apart T2. So we're going to get a T2x. That's going to be T2 cosine theta. And we'll get a T2y equals T2 sine theta in this case. All right. So looking at Newton's second law a little bit, is there anything we can say for sure about any of the forces in this diagram? Yeah. So if I look in my x direction, I should be able to write T1 minus T2 cosine theta equals 0. Of course, I could just write them as being equal. That would also be fine. And in my y direction, I know that mg minus T2 sine theta is going to equal 0. Obviously, I know some numbers. I could just plug things in. Let's be a little bit more daring here. I want to solve for T1 algebraic.
You just put on the other side.
Yeah, so what am I going to solve for? So I want to solve for T1 algebraically. But in order to solve for T1 algebraically, I need to know what T2 is. So let's go ahead and solve for T2. If I solve for T2 here, it's going to be mg divided by sine theta, right?
Can't you just plug in the imperative mg?
Oh, I could. I mean, I could. I like this better. Because then if I plug that in for T2, what happens? I end up with T1 minus mg over sine theta times cosine theta equals 0. So that means that T1 is going to be mg, other one.
Cotangent. I always mix those.
Mg cotangent theta. That's of course not the answer we're looking for. We're going to have to, we could also do mg over tangent theta. That would be fine. 5, remember you can always take gravity as to be 10 over tangent of 30 degrees. And what you get is you get about 86 newtons. You don't have to do it this way. You could also be like, okay, well, this is going to be 50 newtons. And so this is going to be 50 newtons, and then like do some tangents and stuff to work your way around, or do some whatever you want to do with sines and cosines and stuff. But gradually, you're sort of starting here to there and working your way around to 2.
What is graph?
A little different than gravity elsewhere. A little different than gravity elsewhere. All right. 24. Also, are there any between 9 and 24 that we wanted to look at or double check or be
16. I think we got it.
16? We think we got it.
We said it would be.
It is B.
Yes.
It is B. 16 is B. Yeah.
Let's go.
19? Yes, we can definitely do 19. 19 is a classically tricky one. It's a classic tricksy question.
Shrek is Trixie.
Yeah. Anybody who grew up in our generation and watched the Lord of the Rings movies says Trixie.
Oh, is that what that's from?
Trixie hobbitses. All right, so the challenge here, let's take a look at this. We've got a mass, we've got a distance, we've got a force. We're also told that it goes to rest, which means we know the final velocity is nothing, right? We know V final is equal to 0. And we're looking for initial velocity. So actually, let's step back for a second. We're given a final velocity, we're given a distance, and we're looking for an initial velocity. What does this feel like? Now it's kinematics. It looks like a great third kinematics equation, except we're missing a thing to use our third kinematics equation, which is we're missing acceleration. Hey, conveniently, we've got a mass and a force. Maybe we can find acceleration. Here's what not to do. Hey, my force is 11,000 newtons. My mass is 1,000 kilograms times so my acceleration must be 11 meters per second squared.
Wait,
No.
why?
No.
Let's think about the forces on our elevator. What forces are on our elevator?
Gravity
Gravity
and
and tension. So I could go ahead and write
mg.
mg minus t equals ma. Here's the thing. What's mg? Mg is 10,000 newtons. Tension is 11,000 newtons. So the net force is actually only 1,000 newtons.
What
There
did you
is
say?
an 11,000 newton. Right. Sorry. I mean, what were you gonna say?
Wait, what was it?
11,000 newtons. So there is an 11,000 newton force being applied.
You just forgot about tension.
We forgot about gravity, right? The net force causes acceleration, not just individual forces. So remember, basically 10,000 newtons of that tension is going to just stopping gravity. Only the extra 1,000 goes to slowing it down, which means what is my actual acceleration?
1.
Yeah, or -1, if you like. 1 meter per second squared in the upward direction. At which point now we can go ahead and set up.
How's it accelerating?
Oh, well, it had a velocity down, right? Yeah, it had a velocity down, and then its velocity in the downward direction is getting smaller. So it has to get, I guess, if something was falling and you wanted to slow it down, you would need to push it. So the force and the acceleration are up. So now we can go ahead and do VF squared equals V initial squared plus 2a. I'll just go ahead and use delta y here in this case. All right, it stops. We don't know how fast it's going to start. We do know that this is -1, and we're told that this is 8 meters. 2 times 8
It's 16.
is 16. So VI is
Negatives. Wait.
It's 4.
Oh, this is squared.
VI, yeah. So we get VI squared equals 16. So it starts off going 4 meters per second, and then
If this was an FRQ to get points for putting the.
yes, absolutely. Absolutely. So there's a couple of these elevator questions. Elevators are really tricky just because people forget gravity every time. Just you push the elevator down a little bit and you go up, and if you're unlucky and you're at the bottom of the elevator where it's starting to slow down, you can like or no, top of the elevator. Whenever the acceleration is downward. So at the very top of the elevator, as it's slowing down, they jump extra high. 'Cause the elevator is getting pulled down underneath
But
you.
you'll jump less later.
Yes.
So we can scale on the elevator, where it's like there's a scale on it. It's not one of those, it's not one of the things. Yeah.
Well, actually, there is the turtle question. Our friendly turtle here.
Oh, there is.
There is actually a. Oh, where did I put my friendly turtle? Oh, I didn't have my friendly turtle here. Friendly turtle. I guess the important thing to remember about scales is scales read your normal force. So here we got our turtle buddy. Here's the elevator.
Portal, what's your turtle's name? Fred. I feel like you would get a turtle.
Turtle's name.
Michelangelo.
Fred.
You were stealing Ninja Turtle things. I know. What's the point?
Ninja Turtle stole Renaissance painters' names.
That's true. And Renaissance painters' names stole them from real life turtles. I bet they all have pet turtles.
I hope so.
That'd be fun.
That would be
That
great.
fun.
So here's Fred. So Fred is in an elevator. Let's just draw a quick free body diagram for Fred, which is mg down and normal force up. The reason it's an amiable turtle, this is a totally ridiculous side story, is back in that closet is the physics textbook I used in my freshman year at college, which was actually written by one of the people teaching the class. And there's a question in the unit on forces about an amiable turtle in an elevator. And I don't know why, but we found it really funny.
What
Amy-
is it?
Oh, AP Lit people?
I'm an A.
It was in the vocab.
Yeah. Friendly?
But in like an acquaintance way.
Yeah, it has a context also of cooperative or like,
So
yeah.
the turtle is willing to fall.
The turtle is like, yeah, I'll get in the elevator. The turtle's going along for the ride. Yeah. The turtle has not been forced onto the elevator. It's not, yeah,
Would a turtle force on the elevator like change the population?
maybe. All right, so the important thing here is we actually know a little bit of information about gravity here, right? We know that it's got a mass of 0.7 kilograms, which means the force of gravity is
What? Oh, times 7.
so 7 newtons. The normal force is only 5 newtons,
Whoa.
which means which way is the turtle accelerating? The turtle, one of those, it is one of those options.
Down.
Yeah, the turtle is accelerating downward. And I know that because the downward force is stronger than the upward force, right? And that's where you gotta read between the lines a little bit, right? That otherwise you might just be like, oh, there's a normal force 5 newtons up and your turtle's gonna go into the sky. In this case, if I wanted to find the acceleration, what should I do?
Gravity
Yeah, gravity
minus the normal.
minus the normal force is gonna equal ma. 7 minus 5 gives me a net force of 2 newtons, 0.7 kilograms. And if I solve for that, I get the thing. 2.85? Yeah. So it is accelerating downward at about that. Our acceleration is this way. So we don't know what's happening. Maybe the elevator was going up and now it's slowing down to a stop. Or maybe it was at the top floor and is now accelerating downward. If you've been on an elevator though, when you're in this scenario, you suddenly feel a little bit light because your sense of gravity has nothing to do with gravity. Your sense of gravity is the force you feel in your feet.
Is that what happens when you're flying?
Yeah. When you're in free fall, there's gravity, but you don't really feel it.
When you're taking off.
Oh yeah, when you're taking off, you feel pushed down or like pushed forward or pushed back. When you get into an elevator and it goes up, starts to go up to the 3rd floor, you feel pulled down, but what's really happening is the floor is shoving your feet upwards.
And you're not like phasing to the ground because
Yeah, hopefully you're not. Hopefully the floor is solid.
When they ask, there's this one question that asks when the force is the least, that means the least in terms of like the aggregate value of force, not the most negative force, the closest to zero.
In this case, they are, okay.
You want-
In this case, it is both. The normal force will never be down. Because if gravity and the normal force are both down, then you're not really in an elevator so much as you are falling or you're under the elevator, which is bad. Let's actually go take a look at that very question. Because that is a good one to discuss. Let's go ahead and take a look at that very question. This is one that, yeah. All right, we'll think about our turtle friend on the elevator, right? And we're gonna go ahead, it is moving upwards in this case. So I'm gonna go ahead and rewrite this as Fn minus mg equals ma, right? There's some normal force pushing you up. There's gravity pulling you down, but we are moving upwards. Okay. In this case, I'm curious about the normal force. So I'm going to go ahead and solve for the normal force and get mg plus ma. All right. Mg never changes, right? So in order for my normal force to be as small as possible, what do I want to be true about my acceleration? Yeah, as small as possible, or even if I can hack it, negative.
Yeah, wrong.
Maybe if I can hack it, if I can get my acceleration to be negative, my normal force will be even littler than gravity. Is there a place here where my acceleration is as small as possible slash maybe maximally negative? Well, at 4, my acceleration is nothing, right? And if my acceleration is nothing, let's actually, you know what? Let's just do this. If my acceleration is nothing, then that means that my normal force is just equal to mg. That's pretty good, right? What do we think about like a point here?
Well, that's positive.
Yeah, that's a big acceleration, big positive acceleration. So my normal force is going to be pretty big. So probably not that, right?
Wait, how do you know that's a big acceleration?
Yeah, it's a big slope, the velocity timer.
Wait, at the very, oh.
Yeah.
So six.
What if I come to 6? At this point, my acceleration is negative. Right? My acceleration is negative, which means my normal force is going to be very small. My normal force is not going to be negative though, because what will happen first is what happens, I guess, what would happen if I actually had an acceleration which was negative g, as in I'm accelerating downward at a rate g? What would my normal force be? What if I plug in negative g for example?
Zero.
0. That's the case where you're not really on an elevator where the trap door has opened up and now you're just falling. There's no normal force because you're not touching anything and you're just falling. So we're not worried about our normal force being negative, but like we saw with our turtle buddy just a moment ago, my normal force can be smaller than gravity, in which case I get a negative acceleration, right?
There are questions like that.
Yes, this is a question.
No,
This is
I
a
don't think
thing.
there's a trap.
No, but it's a nice way to think
Yeah.
about it. I don't know. Yeah.
What if it's so negative that the elevator is pushing accelerating?
Yeah, okay. Yeah, in that case, if you hit a portion of your graph where your velocity is extremely negative, then yes, perhaps you've hit the ceiling and are being pushed down by the ceiling. But it's pretty specific that it's asking about the normal force from the floor, in which case the normal force from the floor would be nothing.
What if turn the elevator up to the
Then at that point, I think you're violating building codes and you're gonna get your elevator shut down.
Like the one amiable turtle would not be amiable.
Yes. Yes, if we're really, yeah, your turtle will become angry.
You should make an amiable turtle. Oh, you-
Alright.
They're like the perfect physics creature,
They're also good bio creatures. They're
math creatures.
dangerous for little kids.
Are they?
Which is a good thing.
Wait, could little kids not be around turtles?
The very little children, very small children, I think under the age of 2, should not have open access to turtles
Thank
because they
you.
put turtles in their mouth. No, because they
Oh,
put
it's
the
safe
turtles
for
in
the
their mouth.
turtles.
And turtles, no. Turtles often carry salmonella and other bacteria, which isn't dangerous to adults, but if you're a toddler and you put the turtle in your mouth, you get sick. And in fact, the sale of, it is illegal in the United States to sell turtles that are smaller than a certain size because they are like choking and salmonella hazards to small children, because anything that's this big, children will put in their mouth.
Kids just like do that. They just,
breathe in that small.
you can't breathe the turtle.
Breathe, yeah, no vaping turtles.
No.
Breathe, not breathe. I think breathing a turtle.
If you breed them, you have to wait until they're bigger to sell them.
Yeah, so no baby turtles.
You cannot sell baby turtles.
How old are your
Like
kids?
kids.
4, almost 5, and almost 10.
So they could own a turtle.
Yeah, we could own a turtle in theory. We have
Should
chickens
get
though.
a
We have,
beautiful turtle.
Right.
name it Amy.
Amy.
Oh, okay. Are there any other of these forces ones we want to talk about?
24.
No,
Ah. That's great.
anyone but that. Yeah, of course we can do number 20. Number 20. So 20 is a good example of something that I talk about sometimes, which is we've got an equation that sort of looks like it escaped from math class. And when you get a question that looks like it escaped from math class, typically you're going to do a derivative or an integral, or maybe you're going to plug in a value of t or something. In this case, they've given us a velocity function. Bye. And you want to talk about the force. So let's remember, force is ma. If only I had a.
If only.
Oh, you have to.
Oh, the derivative of v is
Yeah.
a.
So it'll be m times the derivative of v, so it'll be 2.
2bt plus,
Nope.
no, oh, because it goes away.
Yeah. And in this case, they want it at time t equals 1. So you're just gonna be like, oh, that's 2 md t1.
T1, wow.
Yeah.
I love derivatives.
So again, just one of those things, whenever you see something that looks like it belongs on the BC calculus exam, you're probably gonna do a BC calculus thing to it. There will be some physics mixed in, but like,
I made it more complicated than it needs to be, but I did get that part. Did get that part.
So you got the right answer, you just.
No,
Oh.
I got that I needed to take a derivative. But
Oh, no,
oh no.
I was supposed. I was supposed to go to the dance concert, but I didn't, and now I'm gonna get yelled at. No, it's fine,
I can send an email or something.
please do.
To whom?
Dr. Kazosi.
Oh, right, she's Dr. Kazusa.
No, but she's gonna be like, oh, you should have just skipped it.
To be like, whoops, I forgot.
I did genuinely forget. I was planning on it too. I was like, oh, I'll go there. It'll take like 2 seconds.
I will send her an email after this. All right. Any other ones were,
Actually,
oh, yeah, 24 had been asked for. 24. Oh, yeah.
20, no,
Um,
24 hours.
so
in a
I
day.
did actually,
In a,
I'm not the world's biggest fan of Rent, but I will say that song has saved me in trivia things before by telling me exactly how many. I've used it for back of the envelope calculations for like,
they made us sing in choir in like 5th grade
The net tension.
for graduation.
all right,
Well, no, it doesn't say net tension.
this is like,
But like, if you.
this is a very good rotation. This is a very good like centripetal forces question. All right. We want to find how fast the student is going. All right, remember, average speed is distance over time, right?
Yeah.
All right.
Yeah.
How far does the student go? So let's say the student goes here, right? We know that they make 2 revolutions per minute, right?
4.
Yeah. So I guess we could do, yeah, so we could do not just 4 pi, we want the actual distance, that's 4 pi radians, but we want the circumference will be 4 pi. Right, so he goes twice around the circle, or you could do 2 pi. 4 pi r, that's 2 times around the circle, and how long does it take?
2 minutes. No minute.
1 minute.
Where did
1
it say
minute.
1 minute?
It says 2 revolutions per minute.
Oh, that's.
Yeah. You could also do it as 2 pi r over, right, over 30. 2 pi r
Good
over 2.
practice to always convert to seconds.
Yes, we do pretty much everything in seconds, plus the answers are in seconds. So if we crunch that out. Numbers. 4 pi times 10 meter, that seems, no, that's fine for a Ferris wheel, I think.
Kind of big, but, you
Uh,
know. No.
I mean, that's 30 feet, 32 feet in radius. So the thing's like almost 70 feet across. That seems about right.
How wide is this room across?
How many tiles are there?
Oh, that's so big. Are these each a foot? About-
Yeah, the tiles are 12 by 12. There's a tiny bit of error because of there's like a little line
a
between them,
little
but they're
That's big. I don't have, I like this room.
I feel like when I put this together that I looked up the approximate radius. In any case, this gives you 2.09 meters per second.
How does this relate to the size of the room?
Okay, we're trying to estimate whether that seems like a reasonable size for.
For a student.
Like, I don't know what 70 feet or 70, yeah, 70 feet is, like, I don't know in my head, so if I know how big the room is, then I know how big the person is.
It's 70% of 100-yard dash. No. Yeah. All right. So we can figure out their speed, and then we want to talk about the bottommost point of the ride. So here we are at the bottom part of the ride, and we want to figure out the normal force on the student from the seat. It's really important, kind of like with the elevator question, to not forget gravity and not to just jump directly into trying to calculate. So let's start with our person and figure out what forces are on them at the bottom. Gravity
No, that's not a force.
and the normal force on the butt. Now, you're correct. We do need a net force, that centripetal force, which is going to point in towards the center of the circle. So what I need is I need Fn minus mg. I need my net force to equal
V squared.
mv squared.
Why do you whisper that in spring Ohm's law? Like, what's the?
Well, first of all, I scream Ohm's law because Mr. O'Neill screams Ohm's law, and I feel obligated to do that.
And you are correct.
I like this because I just want you to think anytime something's moving in a circle, I just want you to feel that voice in your head. In any case, what that tells me is that my normal force is not just mv squared over r, it is in fact mg plus mv squared over r. That is, my normal force has to do two things. It has to overcome gravity, because if it doesn't overcome gravity, you're not on the Ferris wheel anymore. You're falling. It has to overcome gravity and give you an extra boost to move you through that circle, right? And then obviously you can go ahead and calculate that. Although, given that our student has a mass of 50 kilograms, which means that gravity is 500 newtons. If this is gravity plus something, you might be able to guess the answer anyway. What if I'm doing the other one? What if I'm at the top of my ride? I still got gravity and I still have my normal force, right? But this time I'm going to write it a little bit differently. Instead, I'm going to write not Fn minus mg, I'm going to write mg minus Fn. Because I'm interested in gravity winning that fight, because I need that mv squared over r in the downward direction. And what that gives me if I solve for Fn is it gives me mg minus mv squared over r, which is to say, my normal force doesn't have to be that big. Gravity is helping.
What is this, like, what's the centripetal force doing? Is it just flipping them?
The centripetal force, what the centripetal force is doing is it's making sure that you keep moving on that circle, right? In order to move on a circle, you need that force. If you don't have enough force, like let's say they rev up the speed on this thing a whole lot, right? If you don't have enough centripetal force, you will depart the circular path that you were on. That's a little different, but it's you're going to depart a circular path. Yeah.
If you're at the top, is there a normal force?
Yes. If it's going fast enough, so if you've been on a roller coasters are much faster, right?
They're very scary.
If you've been on a roller coaster, as you come across the top of a hill, you'll feel yourself lift out of your seat a little bit, which actually means your normal force is 0 if there's no contact between your butt and the seat. But the feeling of being light at the top of that hill is because as you go faster and faster at the top, that normal force gets smaller and smaller. And again, the sense of gravity that you have is more about the normal force and the feeling on your butt and on your feet. So when you go over that hill, you're feeling that normal force lighten, or in some cases even go to zero if you like, if you're pressing up against the lap bar a little bit. And similarly, when you go down at the bottom of the hill, you feel squished, and that's because your normal force is extra strong.
Ever any of these cases where the normal force would be up?
Well, in this case, the normal force is up at the top, because if you think about you're sitting on the thing, so the normal force would be up. You'd have mg down and the normal force up at the top. But imagine that you were doing like a roller coaster that had a loop. At that point at the top, it might be, if you're actually upside down, it's possible that both forces are down. Yeah.
Thank you.
It sort of depends on where you are relative to the track. That said, if you accidentally flip your normal force up in that case, Newton, the calculations will still take care of you. Because these are vectors, if you accidentally swap the direction of a vector, you might get a negative number for your force, and you're like, oh wait, my normal force came out negative. It should be the other way. So the algebra will take care of it. Any others on the?
Could you go over, I know it's very simple, but 5, for some reason I can't, and 6, sorry.
5 and 6. 5 and 6. Oh, Atwood machines. I love Atwood machines. All right, so Atwood machines come up quite a lot. 5 and 6. Atwood machines come up quite a lot, and it's actually our job quite often to be able to solve them. So let's go ahead. Here's our Atwood machine. Here's our Atwood machine. We're going to go ahead and we've got mass A and mass B. Let's go ahead and just kind of write this out real quick. What we're going to have here is for mass B, we're going to have where'd my good pen go? We're going to have MBG down and tension up. And for my other one, I'll have MAG down and tension up. And if I go ahead, if I think about this, which way is my system gonna rotate? Like which way, what's gonna happen when I let this thing go? Yeah, B is gonna go down and A is gonna go up, right? Because it's heavy. So this pulleys, if you remember, we kind of talked about this. We can think of the positive direction of motion of our system as kind of that way, right? They're always going to move in opposite directions. And if we write out Newton's second law for my guy here, I'm going to get MBG minus T equals MBA. So tension is slowing it down. For my other one, though, I'm going to get tension minus MAG equals its acceleration, because tension is speeding it up. And what we had done sometimes before is having these two things, we would add them. Because they have exactly the same acceleration, right? As one moves up, the other moves down, and they're going to go at the same speed and the same acceleration. Notice if I add them up, what happens to my tension? Yeah, it cancels out. I got a minus T and a plus T. And so what I get is I get MBG minus MAG equals MBA plus MAA. And if I do a little bit of factoring, here I can factor out a G. What I find is that the acceleration of my Atwood machine is going to be MB minus MA all over MB plus MA times G. So this is one of the Atwood machines are actually one of those equations that they really like you to know. And it's one of the things on the checklist is making sure that you're comfortable with Atwood machines. So in this case, if I use my Atwood machine equation, what's the difference between the two masses? Yeah, 2 kilograms. And the sum of the two masses is 10 kilograms. But 2 over 10 is also known as 1/5. You can also sort of think of this as the two gravity forces are fighting each other. MB minus MA times G is sort of the total force. You only get a little bit of extra force because MB only wins by a little bit. But those two forces fighting each other have to move the total mass of the system. So you get kind of a net force divided by a total mass. The system of equations way is a little bit more, I find it to be a little more reliable, but yeah. For number 9, this is kind of one of those classic questions, which is if I'm pulling 800 newtons on a rope, what's its tension? And the answer is 800 newtons. Sometimes you'll see this question phrased in a different way, where you'll be like, I'm going to put 100 Newton weight on either side, and I'm going to like connect them with a string or whatever. Right? What's the tension in the rope? And people want to be like, oh, it's 200 newtons. There's 100 newtons on either side. The tension is only 100 newtons. And the reason it's only 100 newtons is if you think about the free body diagram for just this one, gravity will be 100 newtons down. The tension needs to be 100 newtons back up. So don't be fooled that it's 100 newtons on each side. They don't quite add like that. It's just going to be 100 newtons at each end of the rope. Okay, so if we look at each one individually, right?
MPG minus T.
For this one, gravity is good, right? We know that the heavier one's going to go down, right? So for this one, gravity is pulling it down and tension is kind of slowing it, right? But for this one, I can go ahead and say, hey, it's going to move up. Tension's going to pull it up. And so I can write T minus MAG. And the reason that I'm kind of writing them in opposite directions is because I know for my system that, like, I don't want to just choose down as my direction or just up as my direction. In this case, what's going to happen is as this one goes down, the other one's going to go up. They're always going to, yeah.
But why does it equal?
Oh, we're doing, right, what are we doing? We're doing net force.
But it's for the other one.
Right, well, this is an expression for MB, right?
Oh, okay.
And this is an expression, so we're writing one Newton's second law for each block. It just happens that the tensions are the same and the accelerations are the same. You're not an idiot. That seems both unhelpful and untrue. So, all right. Very good. Any other ones we want to talk about? So next time we're going to try to tackle energy and momentum, and then we'll try to polish off mechanics and do some E&M stuff as well. I'm gonna pause this so that I can upload it.